So, welcome everybody to the second day of the SAS conference, and we have the second invited talk by Daniel Kaestner. And Daniel is a CTO of Absinthe and also one of the founders of the company. He has been working a lot, an awful lot, I would say, on safety security, software security, sorry, and safety in particular. And he's on the working groups of the ISO 26262 and IEC 61508. I never remembered the numbers correctly. And besides those international standards, also is in the MISRA C and another MISRA board about software quality metrics. And these are not international standards, but are, in a sense, de facto standards for the software industry in their fields. Okay, today he will talk about apps interpretation in industry, and that's it.
All right. Thank you for the introduction, and welcome to my talk. Well, as already said, I'm Daniel Kaestner from the company Absinthe. And first of all, I'd like to thank the PC, the organizers, for the invitation to give this presentation here. So it's really a pleasure and an honor for me to be here. Well, today I'll be telling a bit about our experiences when commercializing two different abstract interpretation-based analyzers from two different domains, and talk a bit about, well, the insights we had in this process, which to some degree were a bit surprising, but well, we'll see. Okay, so these, of course, a lot of people were involved in what I'm going to present here. So all the people at Absinthe, for example, and also many people from ENS and Sorbonne. So here I did the slides together with Reinhard Wilhelm and Christian Ferdinand, who are also founders of Absinthe. Maybe I'll just give a brief introduction of the company first. So Absinthe, well, we are a spin-off company from the university in Saarbrücken in Saarland, from the group of Reinhard Wilhelm in programming languages and compiler construction. The company now is 26 years old, so we are around for a while. And the focus of the company really is to develop verification tools for embedded systems with a focus on functional safety. And also, in the latest years, also cybersecurity properties. So it's verification tasks to make sure that these systems work all right and don't harm people. And our customers come from all different industry domains which are related somehow to safety or security requirements. We have about 50 employees at the moment. And this is, well, the list of the products we have. So you can see, okay, well, abstract interpretation comes up quite a lot. So the first tool here is an abstract interpretation-based tools for worst-case execution time analysis. The second one is also abstract interpretation-based analyzer to look at the maximal stack usage, to compute worst-case stack usage of a task. Then the third one is Astrée. So, well, that's a source code analysis on C and these days also C++, again based on abstract interpretation. Then we also have some other tools, mostly in the timing domain, which are not purely abstract interpretation-based, but where there are some components also based on abstract interpretation. And then we also have the ComCert compiler, which of course is a formally verified C compiler, where basically the formal method is theorem proving. And today I'll talk a bit about the first one, so AIT, the worst case execution time analysis, and also about Astrée. So essentially I'm going to tell two stories which are a bit different. So, well, the focus is in both cases is so it's not the same. So in the first, I'm going to focus on the process of insight, of gaining the insight to develop the analysis and how we modeled this. So it's essentially a worst-case execution time analysis, which was not around before. So we had to figure out what the requirements really were and how to model it in a reasonable way, so that it also is usable in practice. So here I'm focusing on a bit on in particular on the variants of abstract interpretation we are using there, the different applications. and to some peculiarities in there. And I'm also talking about some illusions we had where we were quite a bit optimistic at the beginning, and also when we just had pure luck, which is also important. Okay, and essentially the message is that, well, in the end it turned out that it works, and it could only work because we were using formal methods, because, well, we try to really prove properties of programs here, but it's really important to choose the right formal method and apply it in the right way. And then another aspect is, well, what's the cost? What does it mean to develop something which then really will end up in industry and is non-trivial? Okay, so before really going into the topic, well, worst-case execution time analysis obviously is relevant for real-time systems. So in a real-time system, the correctness just not only depends on the logical correctness, but also on the correct timing behavior. So you have real-time task, and if a real-time task misses its deadline, then that's bad. So either it's really a failure which can cause really people to come to harm. So imagine a flight control computer which doesn't react in time, or the steering in a car. In other cases, it's not as severe, but still annoying because it degrades availability. So if you have some assistance system in a car which bails out all the time, then, well, you're not going to be happy with it. And you can also come to harm because of that. And of course, this is something which is known in the safety standards which are around. So this is the view of the ISO 26262. You have a clear requirement. Yes, well, you have to know the an upper estimation of the resources you use, which first means execution time, but then also storage space. So obviously, you should not run into Stack Overflow. That's requirements you find there. And with respect to timing, so there are two different levels where you can reason about time. The first one is the worst-case execution time. So this is really the execution time of a bunch of instructions which form a task, and you want to know how long it takes to execute that on a given hardware without considering interruptions and so on. And at the next level, that's the worst-case response time. Here you are bringing in preemption time when this task is interrupted by another task or gets blocked waiting for some utexes. So if you add all this together, then you have the worst-case response time, so basically the end-to-end time in the system. And here you also have to do some kind of scheduling or schedulability analysis. But the basic ingredient is the worst-case execution time, and that's what we are looking to. All right, so so that means the worst-case execution time problem is, you have some execution platform, a processor, and a program, and then you want to know how long it takes. So this sounds a lot like the halting problem, but I already put the upper bound there. So, of course, computing the exact worst-case execution time is not possible. But computing an upper bound is quite simple, so you could have a constant time algorithm which always says infinite. That's perfectly all right, but will not make people very happy. So, of course, the goal is to have an upper bound of the worst-case execution time which is close to the true behavior. And, that's difficult because it depends on the execution state. So one aspect, of course, is the path inside the program. So the history of the program, so that means that inside the program you have the problem, the combinatorial problem of the different paths. And in addition, you will have the hardware states. So you have to distinguish whether you have a cache hit or a cache miss and so on. And this ends up in a huge state space. All right, so the tool architecture we developed over the years is shown here, and I'm going to tell the story a bit along the line of this chart. So the analysis starts at the executable, so machine code, fully linked executable. We first decode it, compute the call and control flow graph. Then there's a couple of static analysis on it, and then we come to an control flow graph with the results of this annotated here. We do an analysis of the microarchitecture, and then to give the timing information, and then we compute the longest path. Well, So far, so good. So when we started, there were some analyses already available, like interval analysis, abstract interpretation-based interval analysis. We just applied on the machine code level. And also here for path analysis, there was from Lee Malik implicit path enumeration. So essentially, the control flow graph was translated into an integer program, and then you had a maximization problem just to compute the longest path. So that was more or less the starting point. And of course, the most challenging thing or the most interesting part is this microarchitectural design. So here we try to capture what's happening inside a processor. So that means that we want to analyze the machine semantics, and for that we need to develop an abstraction of the machine semantics. So essentially, the goal is to track the state of the machine resources so we can reason about, what's happening inside the architecture. And a very important part of this is the cache analysis. So obviously the cache has a huge impact on execution time. So if you can't predict the cache, you don't even need to start. Okay, and that was the original starting point. So there were the so-called timing schemata, which is basically a structural induction over the program, where, it's very straightforward. So if you have, for example, the conditional statement, then you take the time to evaluate the condition and then compute the maximum of these two paths. Well, if you have an instruction sequence, you sum up the execution time of the instructions. Well, for a load, for example, you then determine the execution time of the load. You already see that the implicit assumption here that the execution times were constant. So at the time you had processors like Motorola 68K. It was the case. Each instruction had a fixed execution time, so the problem was rather simple. But then people started using caches, and then, of course, the execution time of an instruction is not constant anymore. And first work here in this area was, for example, from Frank Müller and Sang-Yul Min. So here there was a cache analysis for direct caches, which was the first attempt to look into this, and Sang-Yul did an extension of timing schemes to look at caches. And the problem was that this was typically limited or not generalized for set associative or fully associative caches. So there was no solution around to deal with this. And that was the starting point of our work. So it was essentially the research work of Christian Ferdinand. And the goal was that we want to classify memory accesses in the program as always a cache hit or always a cache miss. And the idea would be was that it should be possible to support the cache architectures which were around. So like fully associative caches where all blocks can go into the same line, or set associative caches where you had a set of blocks into which the cache memory blocks were sorted. And then it turned out that there is a very efficient abstract domain to represent the cache, and the idea is basically to look at the to compute an abstraction of the execution state at the end of an instruction trace. And that means that we map memory blocks to some cache block and associate it also with its age inside the given cache line. So the cache eviction strategies least recently used, for example, work like that the oldest element of the cache is evicted. So having this concept of age in the cache is quite important. Okay, so that was the central idea, and it's a very efficient representation. I'm going to come to this in a minute. A second aspect which was important, so the focus of the original analysis was to have a must analysis, so that we can guarantee whether a block is in the cache. We had a complement that essentially a may analysis, so if you know that the block may not be in the cache, you know it can't be in the cache. That was the second aspect, and the third aspect is the persistence. So, you can define a memory block to be persistent if if all accesses to this block will be in the cache after it has been accessed once, then you know that it will not trigger any cache misses later on, and then you can bound the number of cache loads in a program segment. Okay, so so we had this the must analysis, the may analysis, and also some concept of persistence. But still, when applying it for the first time, the overestimations were quite big. And when looking into this, it turns out that the cache in that case, later it's a property with also other architecture components have. They tend to take some time to stabilize. So let's just look at the standard fixed point iteration. So we will come, so let's say this is the program flow, then you hit a loop, and then of course in the first iteration of the loop, the memory accesses will be cache miss. Right, and then you go in the next iteration of the loop, and then when you compute the join in the must analysis, well, you join with it's not in the cache, so nothing is in the cache. And then you execute each iteration of the loop under the assumption that you only have cache misses, which of course is absolutely not what happens. And so the idea, with hindsight, it's pretty obvious, but the idea is then, to do some concept of virtual unrolling. So basically you peel off the first iterations of the loop and then only do the union afterwards. And then, of course, you can distinguish the iterations where the cache is being reloaded or loaded from the iterations where it's stable. And so that was also an important point. Okay, so that was basically the starting point. So this was essentially the dissertation of Christian. It was in '97, and then, we thought, okay, that the problem is solved, and so let's try to. So there's really something new. Let's try to build a company and sell it. So that was in '98. And it turns out that it was not really the case. So the first point where reality hit was that it works very nice with least recently used caches, but they were rarely used in industry because they are kind of expensive to implement. So people are using like pseudo LRU strategy, for example, where it's a bit more difficult. And then, it's not the cache alone which has to be taken into account, but quite a bit more. Okay, so it turns out that there was still some work to do, and that was the starting point of a research project called the Daedalus, together with Airbus, where Patrick Couzeau was the coordinator, and that was really an opportunity to find out the points which were still missing. All right, so the first idea was, okay, we had a cache analysis with a must and a may analysis, so where we could predict the cache behavior alone pretty well. And so the prerequisite for coming up to this is that we were quite familiar with this formal methods background, worked with abstract interpretation a lot. So that was really the idea which enabled this. Okay, and then if you look at some at the processor architectures which are around, then you will find out that there is a lot of speculative hardware features. The caches are not the only ones. You have a pipelined architecture where you have different stages in the pipeline. The instruction proceed through. Position inside the pipeline can be reordered. There are out-of-order execution pipelines. There are things like branch prediction, prefetching, and some more aspects. And you have the caches, but you also have prefetch buffers and so on. And so all of this plays together, and the effect is, that the execution time really depends a lot of, what has happened before. And it's not just the cache. So here there's a bit of an illustration. So let's just take these three machine instructions on something like the 68K. Instruction execution time was constant. So best case was the same as worst case. Then there were, let's say, some flash accesses which were buffered. So here you could have already a difference between the best case and the worst case for these 3 instructions here. And on something, well, realistic at around the year 2000, the difference, or just for these 3 instructions, could be a factor of more than 100, depending on whether it has been in the cache and what else has happened before. So essentially, these speculative hardware features can cause timing accidents. Like if you hit the cache, well, then if you access a memory block, then the accident is that it will not be in the cache. And, well, that causes a penalty. So that's one way to talk about it. And these kind of timing accidents could be cache misses, stalls in the pipelines, branch mispredictions, or just collisions on the bus. Then if you have DRAM memory refreshes, misses in a translation look-aside buffer, and so on. All right, and well, what this abstract interpretation model can do basically very efficiently is to analyze the execution history to a certain program point. And well, the idea is to be able to prove that certain timing accidents will never happen. So if you know then then well you do not have to take into account the penalty for the timing penalty for such a timing accident to happen. So you try to prove that certain bad states cannot happen. Okay, and so that's now the methodological view. So here in this block, there is some abstract interpretation-based analysis, so a value analysis where we, well, traditionally compute the values for registers, memory cells, and so on, a loop-bound analysis, and from this, we try to determine infeasible paths, so that, of course, they don't have to be considered. And then the core is this abstract interpretation-based analysis of the microarchitectural state centered around the cache analysis. And well, the worst-case path, so this gives the timing information, and then again, worst-case path can be computed by integer programming. All right, and then the next step would be really to look at the pipeline, because all the other stuff, the speculative mechanisms are somehow integrated in the pipeline. So that was some other dissertation from another founder of Absint, Stefan Thesing. So here, well, it was an abstract interpretation-based modeling of the pipeline. And well, it essentially was a power set domain. So this is something which was quite expensive. But it did work. And, well, the platforms, the processors we were looking at in the Daedalus project was Motorola Coalfire and PowerPC 755. So, and here there were also the less predictable cache replacement strategies, which also had to be modeled. And we also found a modeling for this, but the precision was a bit reduced. Okay, so so basically this pipeline analysis then really bound the different aspects together and made it possible to also model the other predictive speculative features. So we had the first paper where we presented the entire approach was at an MSoft conference in 2001, which then 20 years later got the Test of Time award. So as a quite influential paper, so it really opened a lot of subsequent research. So also from, let's say, the university in Saarbrücken, there was a kind of research which originated from this was to classify caches and come up with general classification also of architectures, to which degree they are timing predictable. That was Jan Reinecke. It essentially originated from this as well. Okay, so in the pipeline analysis, so the power set domain is necessary because you cannot easily prune states which you can consider irrelevant. So, for example, you do not. So, if in a pseudo least recently used cache strategy, like you have with PowerPC, you can assume that the empty cache is the worst case state, right? So, the worst case cache state for some instruction sequence is some pre-filled cache, which depends on what instructions you are trying to execute. So, you cannot just assume that the empty cache is the worst case. And neither you can assume that a cache miss is the worst case. So it can be that, for example, if you have a pipeline and you have a condition, well, if you have a cache miss at a program point before, it takes some time, the pipeline is stalled, and when you evaluate the arguments, you know which branch you will take. And if you had a cache hit, then you would have run into the condition very fast. Operands might not have been available. You could have speculated into the wrong path, which triggered a cascade of further cache misses. So that means you cannot really decide what you can throw away, and that makes it expensive. And then we tried also to look into model checking. So that was Stefan Wilhelm. He tried to do a model checking variant of the pipeline analysis. But there was a trouble that it was very hard to connect the abstract interpretation and the model checking. And it also, from a perspective of efficiency, was not really better. Okay, so we did not follow this model checking approach further. A slightly different view is that, well, we tried to analyze different difficult architectures, so we also developed a pipeline which could be analyzed very well and suggested it to the hardware community. And, well, nobody used it, so that was a pity, but it would have made life quite easy. Well, it's not entirely correct. So the Calray architecture is designed with a very predictable pipeline. So that would be an example of where it was heard. Okay, so that means that so for the precision, really, the caches, the pipelines, and so on have to be analyzed together. Trouble is that there is no compact cache domain if you try a model checking approach, and vice versa. In the if you look at the pipeline, well, then you can't really do a lot better than a power set domain in abstract interpretation. Okay, so and well, at this stage, with the optimizations we did in the Daedalus project, in the end we really could come up with a working analysis of the cold fire processor with a 15% overestimation, which was very good and better than what Airbus has used before with the safety margins they applied, and also likewise on the PowerPC 755. So that was then very nice, and then we thought, okay, that's it. Now we really have analyzed two microprocessors which were widely in use and could make Airbus happy, so they were using this also. And we thought, okay, now we can get rich. We just sell this everywhere, and that's it. But unfortunately, that was not really the case because, well, there is really a reservation against using formal methods. So it's something many people don't understand, and using something people don't understand, there is a very big resistance against that. You see it in Europe, but even more in the US. So that's kind of a trouble. And I'm going to talk also about this in a minute a bit more. And then there is a huge amount of different hardware configurations. So there are lots of processors. Processors can be configured in different ways. So in the end, it's not something you have what everybody uses. So as of today, I think we have more than 25 different target architectures we support in the timing analysis with a lot of different compilers. So that means that for a new processor, this has to be instantiated, which takes a lot of effort. Okay, so that's basically how it looks like. So the commercial side of it, you can see it here. So we start from the executable. You can specify tasks or interrupt service routines. We compute the worst case execution time per task or interrupt service routine with visualization, the information of the critical path. And then there are lots of tool couplings, for example, with SCADE and other model-biased design tools, with scheduling tools. and also, let's say, with Jenkins, so people can easily integrate it and automate it. All right, and another important aspect is, let's say, the confidence. So people have to trust the results, and yes, with abstract interpretation you can prove that the model is correct, but the question is still whether you have the right model. So that's essentially so philosophically viewed, this is the question of the logic versus epistemic doubt. So the logic doubt is solved by this, but the epistemic doubt, what about the environment? Do you really capture the real system which is running? That's something else. And it turned out that we had to spend a lot of effort in order to deal with this. So yes, the soundness proof is one aspect, but then what about the implementation? So you have to have some confidence that the implementation is all right. So what we used here is basically we could generate the implementations of the analyzer from a specification. So that was the program analyzer generator pack at the time. And then we have to validate our models. So, and binding that together, there are validation suites we can run where we can really check that the implementation of the tool corresponds to what we think it should do. And it was also necessary to, let's say, document our development processes and say, okay, we meet the requirements you have for safety critical systems. And to validate the model, well, the trivial way is for execution time analysis. You run a task, and then the execution time you observe must be bigger than the worst case execution time bound we compute. But that's not a very deep view. So you could have underestimations which are just shadowed by overestimations in other places. So you can't really rely on that. So what we now do is to do an in-depth validation. So basically, the analysis essentially predicts all execution paths with all hardware states, which we think can happen. And then these hardware states will correspond to observable events, and then all these events must be predicted by the model. So this slide is pretty lengthy. So essentially, we look at performance monitoring features like log ticks, cache misses, mispredicted branches, at bus traces and instruction traces, from which we collect all these informations, and we instrument the model to emit the, let's say, abstract traces for these different types. So we come up with a prediction graph, and then any real observable sequence of events then must be contained in this prediction graph in exactly the same order. And then we can say, okay, now we have reasonably validated the model. And so typically we start from the hardware manual of the processor, and well, often you have, or not often, but it can happen that you have silicon bugs and the architecture doesn't correspond to the model or to the manual, or the manual just was wrong. And of course, we can't model the manual, we have to model the processor. So, and we also learned that it's a different thing. All right, so I mentioned some research projects, and that, well, all this was quite costly, and we were quite happy that we managed to get research projects where we could fund all these developments. And the cooperation with Airbus was also very good. So because we had a customer which was really interested and supported us, pointed always out where some problems were in a cooperative way. Okay, then we could basically generalize the approach. So the same tool architecture can be used for stack analysis as well. And then I have the slide, but I'm not going into any kind of detail here. There are multi-core processes around where you have interferences between the core where the state space really explodes, and then you cannot have a static guarantee anymore. So in that case, it's just, let's say, the path analysis which remains, and the value analysis, loop-bound analysis, and so on. But for these kind of multi-core processes, you have to combine it with traces. But that also is based on the same tool architecture. So what we did for this worst case execution time analysis for predictable processes could also be used in other areas. So to sum this up, so I've talked a lot now about how we came to this. So it was basically kind of a new research area, how we came to the solution. So we had some ingredients we started with. and did the rest. And let's say the effort to come really to the first working prototype was about 15 to 20 years, person years. And we started with a very good background in formal methods to do this. And so now this is a massively more. There is a lot more effort which is which went into this. This was just the initial start. So if you want to really try something out in practice, you should plan for some time. But then it can also be applied to other cases. Now I'd like to tell a slightly different story. So here now it's about Astrée, and here we had a cooperation with the ENS. So basically, when Astrée had a working prototype, they Xavier and Jérôme, so the group of Patrick, considered usable. We basically started cooperating there to do the commercialization of the tool. So I guess a similar story than what I just told with Astrée, you can have from Xavier and Jérôme and Antoine if he's here. So, and this basically now starts after this. So if there is already a viable prototype around, which works pretty well, what else do you need to do to make the customers happy? So in case of the timing analysis, it was a bit interwoven, and here there is a bit, it's more clearly separated. So what I'm now going to tell about is, well, what we did since starting with the original state to, let's say, to meet the requirements or the expectations of the customers, where we had to extend the analyzer, and what about automation and scalability. And here, let's say, here the message is, well, if you want to have it out in practice, of course, the analysis has to be precise. It must be automated as much as possible, and it must be easy to use. Yes, and it also turned out that safety norms are a very important motivator for all of this, also with the timing analysis. And this is also something I'm going to talk a bit more about. Okay, so the development of Astrée started around 2000 in the group of Patrick and Raja Couzeau at ENS. So some of the original authors are sitting in the audience here right now. And 2009, let's say, we went to Paris for half a year and started to learn a bit about Astrée, and then started a commercial development of it, but still with a very good cooperation with the guys from ENS. And the initial state we did was so this was a chart I basically stole from a presentation of Antoine in 2010. Well, at that time, Astrée, it stands for Analyseur Statique de Logiciel Toriel Embarqué. It looks for the absence of runtime errors on a subset of C. It's semantic-based sound, and well, if you have a synchronous real-time system, you can analyze it as without any false alarms. So that's already very nice. So that essentially was the starting point. Well, it was a command line tool. So you could invoke the analyzer, could indicate which abstract domains you wanted to activate, supplied a C program, got the result as a text file, which was fine. And there was also a first, let's say, rudimentary graphical user interface. So that was more or less the start. And then I grouped what we did in the years afterwards in different categories and tried to collect a bit where we spent some effort. And one big part was usability. And of course, to some degree, it's trivial. So you have people who can't operate a command shell. So yes, you have to have a user interface, a graphical user interface, but it goes deeper than that. Because so runtime errors at the C language level means undefined, unspecified behaviors. So it's where you have a lack or let's say trouble with the language definition. So that's the difficult areas of the programming language. And then you have an analyzer which can have false alarms. The analyzer, what it does internally is also very complex. So you have a complex thing which reasons about other complex things, and if you want users, people to understand this, you have to spend quite some effort. Okay, well, then rather mechanically, the preprocessing was separate before, so you had to run the preprocessor alone. So some people are not able to do this, so we integrated the preprocessor into Astrée, generalized it to more platforms. And then there are also, like similar to AIT, a lot of couplings to other development tools. So if you do model-based development, it's nice if you can just push a button and get a result, and ideally also get the findings connected to your model elements. This was rather interesting. So there are some Astrée directives you can influence. So basically you can communicate with the analyzer to, let's say, locally increase the precision of the analysis. So you can parameterize the abstract domains essentially. And so by default you just wrote it in the code. But then there are people where the code was frozen, so it was impossible to change the code anymore. And of course, with model-based code generation, you don't have the source code at all. You have a model from which the code is generated, so you cannot put anything in the code. So we developed basically a mechanism to specify this stuff outside of the code itself, and that was really also a prerequisite for some domains to be applicable at all. Well, then you have some findings, and often, well, you just want to say, okay, it's a false alarm or it's justified. I have to think about how to repair it. That was also something. And then the build process can be very complex. So we tried also to simplify this, for example, by importing it from a JSON compilation database, so that you don't have to collect all the include parse macro definitions, which can be quite some work in a complex project. Okay, then formal requirements, like with AIT, you have to demonstrate that the tool works all right. So there has to be a qualification support kit to show that, in addition to the proofs, the soundness proofs, that it really works all right. Yeah, we also had to extend the content. So from the first sequential semantics, Antoine did an extension to concurrent, to interleaving semantics, so which really broadened the capabilities of the analyzer a lot. So it was possible to talk about data races, deadlocks, other concurrency issues, and could also completely model the API of some operating system norms like OSEC, AutoSAR, RINC. I'm going to show this in a bit more detail later as well. Then in particular for cybersecurity, you often have, let's say, properties where you want to check where information flows to. So that can be handled by a taint analysis. So we incorporated basically a general taint analysis into Astrée, that you can say, okay, if I have a sense of corruption here or somebody tampers with my inputs, which parts of the program could be affected in a user configurable way. Code guideline checking, like MISRA, C, well, that's not rocket science, but it's something people have to do. And in a framework like Astrée, it's easy to do, and it would be silly not to do it. But it's also a lot of work. And then the data and control flow analysis is a verification topic of its own, so we also had specific support for that. And then another small detail is now that people can work reasonably well with C. They decided, oh, well, why not move to C++, which opens up another completely new can of worms. Okay, then there is some application-specific stuff like peculiarities of some code generators. We also have some, let's say, vulnerabilities we are targeting out of the box. We had to work a lot about tuning the precision to reduce the false alarm rate further, for example, by a state machine domain, interpolation domain, and some other abstract domains we brought into the analyzer later. And essentially, a very big part of work was also to really get it run on large-scale software, because even in embedded systems, the software size is becoming huge. Okay, so that would be, well, let's say the commercial view of it. I mentioned it all, so that's basically the summary. And to show how it works now in practice, I'm going to quote from a presentation I had this year at the SAE conference, where basically we looked at how Astrée is run on integration analysis of automotive software, so in entire control units with a multi-threaded analysis. and what let's say the results are on these kinds of code and how they look at all. Okay, so I've mentioned the interleaving semantics for talking about concurrent threads of execution. So the foundation is an abstract interpretation-based interleaving analysis. And well, if you want to talk about these concurrent issues, originally they were not in the C language. So you had to have primitives telling the analyzer when these things happen, like when a process or a thread is created, when you lock or release a mutex, when you disable or enable all interrupts. So you have primitives in Astrée which communicate these, let's say, operating system events to the analyzer. Okay, and then if you have a concrete operating system, well, then you can build an abstract library. So you have an API, for example, in AutoSAR. If you want to lock a mutex, it's get resource. So you can implement it with these kinds of primitives and also do some bookkeeping. So you can report alarms like lock without unlock or double lock, that you can also find some defects in the modeling. And for users, it means that they can just run the analysis on such an OS without any change. And then in AutoSAR, you do not create the processes explicitly. You have an operating system generator, which generates, let's say, tables for the tasks automatically. So this is not part of the C code. So if you want to do this automatically, it's necessary to understand this XML specification, which is absolutely unreadable, can be megabytes just text. And so we implement essentially a converter where we extract the relevant information from there. And that means what tasks we have. So in this automotive world, the tasks are then grouped on applications. The applications are assigned to cores. Process control is done by alarms and events. Of course, task priorities have to be known, whether the tasks are priority, preemptible. Then you have to know about the mutex locks or the spin locks, and so on. So this is automatically extracted. And that means if you have such an AutoSAR system, essentially you can run the analysis out of the box. And then I've mentioned that it's possible to interact with the precision of the analyzer. So essentially this, Xavier did a lot of work on this. That's essentially by partitioning execution traces. So there are different aspects, value partitioning or control partitioning. We also generalize it to state machines. So you can also partition state machine states. And also with loop unrolling, you can say, okay, you partition different loop iterations. And these, there are also primitives to control this. For example, there is one primitive where you say, okay, this is the state variable of some state machine, and then an Astrée does an automatic partitioning according to the automaton states. And it's quite helpful to use this because you can tune the precision of the analysis then to really concrete software project. Okay. And this is how it looks. So that's we just took 10 automotive projects. That's integration projects, and of course we can't tell anything about what they were doing or from which vendor they came. And you see that the code range. So nothing is below 1 million lines of code. So it's I think it starts at 3, goes to 40 here in this table, and the biggest project we saw was 100 million lines of code, where we count the pre-processed lines of code. So the software size is pretty gigantic. And so you can see here the time for the analysis typically ranges around a day, sometimes a bit more, sometimes a bit less. And memory consumption really is manageable for this kind of software. And in terms of runtime errors, let's say, so sometimes Astrée can say, okay, there is a definite runtime error when you're sure that in a given execution context you will run into a runtime error. And here, that's some breakdown. So you have an average of 14 or 15 alarms per million lines of pre-processed code. So with a bit less certainty, general alarms about runtime errors. So here there are around 733 per million lines of code. So you can see that the precision is, so that's still quite a number of alarms, but given the software size, it's reasonable. And data races, so here we can see, okay, objects we could prove to be free of races, range between, let's say, 70 and 99%. Average is 85. This is quite high, but for the number collection, we did not distinguish. Well, for example, we treated an array as an entire as one object, and of course, Astrée can distinguish cells in this array elements and say, okay, on this particular cell there is a data race and on others not. So here we are, let's say, we are making it look a bit worse. So not you don't have 15% on all the objects in data races on all the objects in automotive code. Okay, and now this is the contribution from this precision tuning. So here, and of course, it's not possible to spend infinite amount of works in doing this. So you could see here, that's the number of directions we inserted. So here it was just about 50. I think here there were about 1,000 of these directives. And then we tracked what the benefit of it was, how we really could improve the analyzer or the results by this. So here we said, okay, how much we could reduce the number of runtime error alarms, data race alarms, and what the change in time and memory consumption was. And that was a bit surprising at first because, well, when tuning, so typically you increase the precision of the analyzer by these directives. So the expectation would have been that, well, it makes the analysis more expensive. But in the end, on most cases, it's actually not true. By making the analyzer more precise, you reduce analysis time and also memory consumption. Because essentially what happens is that you strip away spurious contexts you should not have tried to follow at all. And by cutting away those, you make the analyzer more efficient. So that's so on average, we could reduce the number of alarms by 20%, number of races by 8%. Well, but still sometimes, so I think I can't read it here, but somewhere so in this example, for example, analysis time increased quite a lot and also memory consumption, so it can also happen. Okay, so that's how it looks on realistic projects. So just to give a feedback on how complex these kinds of applications are. And now let's say to look at the market. Well, if you talk to customers, then well, from a verification community, so or a program analysis community, we think this is an important thing, but actually people are not excited about this. So it's well, to put it carefully, not exciting or perceived as a burden, or you could also say a pain in the ass. And people really don't like this a lot, and they're also often not considering it very important. So it's more work. If you come along with a formal method, it's something new, people don't really understand. And another psychological aspect is, well, if you start doing something like this, you admit that what you did before was not perfect, and it could be seen as your fault. So that also is some aspect. So what it means is that, well, it's not really a selling point. You don't sell a Mercedes and says, okay, my brakes crash less often than with Volkswagen, although it might be correct, but that's not how, let's say, all this stuff is sold under the assumption that it works. And then you can't say, well, for me it works more often than for you. Yes, then also a level of expertise is a problem. So, well, people have to have some understanding to operate these kinds of tools. And, well, so what is an accepted benefit is, well, if you fix bugs which are escalated. If you had people chasing a data race for weeks with the entire team, they are very happy to buy an analyzer and don't ask about the cost, but otherwise it's difficult. Automation is important. If it helps people reduce the effort to, well, if they have to do something and they can save time by using a tool, then it's also good, because then in the end you're saving money. And this is where we come to the safety norms. They are important because they essentially define what it means to develop a software with due diligence. So it's what you really should do if you write a software which could kill or harm people, what you should do. And if you have a requirement that you have to do this somehow, then that's a big step. And then it basically becomes an insurance. They have to tick a box, oh, I have to look at the control flow, so let's do control flow analysis. And that kind of gets rid of, oh, why should I do this at all? And okay, so that's why these safety norms are important. Avionics, so this is the view of the DO178C, which is very nice. So that's a nicely written standard, although it's not, if you read it, it's not very accessible. So it means, well, it says, well, with testing, you cannot show the absence of errors. That's already quite an insight. And it defines software verification process. It says, yeah, well, you can use formal methods if you like. It lists abstract interpretation along with theory improving and model checking as formal verification methods, which you can use. Mostly the standards say the standard verification technique is testing, and if you want to use something else, people are not happy, you have to do additional justification why you do it. Okay, so that's the formal method supplement. So you can see all these kinds of errors I've talked about are deemed critical, so you have to deal with them, and you can use formal methods to reason about them. So that's the aerospace view. Now let's have a look at automotive. Oh, this got collapsed by the standard slide, by the aspect ratio. It's quite interesting. So here you have so that's the method you can use for software unit verification. So there are formal verification, and then you find control flow analysis, data flow analysis, static code analysis, and static analysis based on abstract interpretation with as different methods with different levels of recommendations. And if you look at the definition of abstract interpretation, so it's a collective term for extended static analysis, which introduces analysis such as extending the compiler parse tree by adding semantic information, which can be checked against violation of defined rules, and so on. So, well, I would say the definition is not really optimal, and so there is still, let's say, some leeway to improve these standards. And if you look at the railway norm, actually there are two of them. Well, they talk about formal methods, but they don't know about abstract interpretation. It's not even listed. So that means that, let's say, that there is kind of a gap between the scientific community and what you see in these standards, and it's really important to interact with the standard people and make sure that, let's say, if there are some verification techniques which can be used, well, people should know about it, and it should somehow end up in these standards, because, well, from, let's say, from an academic perspective, if you develop something, if it's not in the standards, then it's already an argument against not using it in practice. So I would encourage everybody who has some spare time to try and join these committees and explain people about, let's say, the verification methodology you are doing and why it could be good to do it. Okay, general outlook. So software becomes really more and more complex. It really explodes. Cybersecurity becomes more and more important because all the classical safety systems are opening up. And are communicating with one another, then, well, all this AI stuff, the neural networks, machine learning, is kind of disruptive. And that's also interesting because people are using them all over and then are saying, okay, there's the traditional safety arguments don't work here anymore. So, but we can't do it without, so let's just do it with them. And then why should we do all the stuff for the rest? So basically, the traditional formal verification methods you could apply on deterministic systems are becoming questioned. So that's really bad. And then also you have increasingly dynamic behavior like programming language like C++, or you start to see people running in POSIX or Linux environments, or even more service-oriented architectures. That's the new automotive software architecture. Yes, and then of course the safety of the, let's say, neural networks, machine learning, it's an open question of its own. Okay, so then I'm more or less in time. So let me conclude. So I try to give an overview of, let's say, what we did in the past years. So we try to, let's say, commercialize formal method-based tools for industrial use. I summed up some of our experiences. So, of course, so if you look at abstract interpretations, these kinds of analyzers really have a benefit. They can prove things people could not prove before. But, well, bringing this to market is really some significant, takes some significant cost. So you should calculate some years before you start earning some money with it. It's essential to let's say to bring users to use the tools actually. So that's also something not to be underestimated. And again, the role of these safety or cybersecurity norms is essential because really people tend to do what's written there, and if it's not written there, you have you're in trouble. All right, then. Thank you for your attention. And in case of any questions.
So if there are questions, even on the Discord.
Mm-hmm.
Hey, so great talk. I've done some more static analysis in industry, and one of the things that I've always found difficult was iterating with the people using my tools. Mm-hmm. In particular, I developed a tool that would find slow spots in Android applications, and it found tens of thousands of places where the safety property was violated. Mm-hmm. But the process of like iterating with the developers who were using my tool took long enough that they eventually didn't continue using that tool. So what I was curious about is how do you keep the people that you're working with continually engaged as you refine the safety properties and tailor it to the kinds of properties that they care about the most?
Yes. So this is something we really try to understand what the safety properties are. People are really interested in and see how they can be addressed from inside the tool and whether we can improve it. So maybe one example was, let's say, the data and control flow analysis. So in the DO standard now talks a lot about data and control coupling. So essentially so this goes beyond the usual code coverage metrics. You try to measure somehow how different software components can interact with one another, and whether you, in the testing you did, you exerted all component interactions you could have. So it's not just about, let's say, having coverage of the code, but also coverage from different components. And so this is something which, of course, we can support with Astrée. So if people want to do about the data and control coupling, they have to know at first what at all they can have. And with Astrée, we could compute an overestimation of this data and control coupling. And well, essentially what it meant is that we had to introduce this concept of software components. So it's not about just the pure language anymore. So you can specify now what you consider a component, bunch of function or files or whatever, and then you try to compute the dependencies between these components. And then you have some insight about the data and control coupling, what you could possibly have as an overestimation, and then with that information you can look at your testing. So that was a classical example where people asked, I have to do this verification property, but the tool does something similar, but it's not really what I need, and then we try to support that better.
Thank you.
Other questions?
Hey, thanks for the talk. You showed this nice table with how many sort of potential bugs you found. Mm-hmm. Do you have any idea of how many of those were actually bugs and how many of them were false alarms?
No, not really. So, I mean, the software size is absolutely huge. And of course, there are some obvious things. So yes, we did find out-of-bound array accesses or dangling pointers, which were more or less trivial to identify as true findings. But then it really becomes difficult. So what we also have in this, let's say, concurrent analysis, that we can separate between different execution stages. So, for example, you could have just initialization tasks running, and when they have finished, then the normal working tasks start of them is synchronized, so you can have different phases of execution. You can also model with Astrée. And now let's say you look at the data race, you see there are 2 or 3 processes involved, and Astrée reports a data race. But it is a true defect could be that there is some mechanism to make sure that one of them, that they can't really overlap at all, or that you have some, let's say, some timing properties in the system which would avoid a collision from happening at the same time. So is this a real defect then or not? So really finding out can be quite some effort. And also with the examples I've shown, we got the code, so we could look at it, but it's really big piece of code. And from the vendors themselves, we don't have information. They don't tell us we have found this and that true bugs. The rest was irrelevant. They don't tell us. But it's a good question. Yes.
Yeah. So I have a question about in IIT you have a lot of analysis which depend on the history for the cache and pipeline analysis, and I was wondering because in real-time systems often you use a preemptive scheduling. So how does this affect the fact that you can compute history-based analysis when the history can be flushed at any time?
So the standard AIT analysis basically assumes that there are no interruption from the outside. So it just focuses on an uninterrupted execution of the task. And then if you have, let's say, preemptions, then you have to look at them in the scheduling analysis. So the scheduling analysis would compute critical instance, how many interruptions you could have in the worst case. And then another contribution of the static analysis is that you could calculate some cache-related preemption delay. So if what the worst case preemption costs would be that this and that amount of cache lines would be evicted. So you have some concept of worst case preemptions costs you could have. And if you know you can be preempted at worst 4 times, then you can apply this additional cost in the scheduling analysis. But this would be something which is not part of the analysis itself. So you have the scheduling analysis around the response time analysis and would add this as an overhead. So that's something where you have support, let's say, from inside the tool and also other stuff like, let's say, if you have DRAM refreshes, you can more or less calculate some general overhead and also add it to that.
So we are a bit late on the schedule. Last question.
Thank you. Thanks a lot for a very rich talk. I have a question concerning the certification of cybersecurity properties, which seems to be a bit of a different game because it's more open-ended in the sense that I think you first have to specify what is your threat model actually. And then it's also still very process-oriented as far as I understand, that you have to go and be able to convince someone that you've followed the right steps when you implement your protection mechanisms, which is perhaps also where static analysis can help, but I don't know if you have any thoughts about this.
Well, so it is also on a theoretical level. Cybersecurity is more difficult because you tend to have hyper properties, and in safety you have rather normal, so trace properties. Normal properties, but of course, it's for cybersecurity is more difficult because it's not really clear. So there can be side channel attacks, and you just have to. So there are some vulnerabilities. That's the easy part. It's clear that some things constitute vulnerabilities. You can find those, and you can also try to assess the effect of certain side channel attacks, like the Spectre or vulnerabilities that's rooted in there. But whether that's enough or not, so I don't think you can really say, okay, you have proved to be safe from cybersecurity attacks. You can just say, I've excluded this vulnerability and this particular scenario, I can prove it will not happen. Under the assumptions I could make so far.
So thank you very much. We'll thank you, Daniel, again.
Yes.